There we go. Guess everybody can hear me okay? All right, well, the topic today is turning seawater into drinking water. And I'm presently working on the permitting for the city of Corpus Christi for the first seawater desalination plant in Texas. And so I wanted to use this as an educational tool and also to kind of introduce what we're doing in Corpus Christi. The Texas Water Plan, which is a plan that's put out every 5 years, has a statement that says the primary message of the state water plan is a simple one. In serious drought conditions, Texas does not and will not have enough water to meet the needs of its people, its businesses, and its industries, and its agricultural enterprises. This is an important issue as we get in, especially for Georgetown. We're really looking at long-range water supply. One of my favorite quotes is by John F. Kennedy, where he said, if we could ever competitively at a cheap rate get fresh water from seawater, that would be the long-range interest of humanity and would dwarf any other scientific accomplishments. And I fully believe that, and we're getting very, very close to that coming true. Also, the World Meteorology Organization projects that by 2050, there'll be 5 billion people who will not have adequate access to available water supply. So this is a issue that I think affects all of us. Okay, what has held back seawater desalination? What's the cost? It's expensive. Probably everybody's heard it's expensive. By 1970, the cost of seawater desalination is about $19 per 1,000 gallons that you produce. Today, we can get it under $4 per 1,000 gallons produced, an 80% reduction in the cost of the seawater for the last 50 years. So now it's getting down where it's competitive with other types of water supply sources, especially like in Corpus. We had to go hundreds of miles to the Colorado River to bring that water in to the city. We built 2 reservoirs. Those are very expensive. So this is becoming economically viable. Also, another important feature of desalination is the energy cost. What you're going to learn is that when we desalinate, we have a membrane. And we're going to push salt water through that membrane. And that membrane is so tight, it's 1/millionth the diameter of a human hair. Well, it will stop the ions. It will reject the sodium ions, the calcium ions, chloride ions. But it takes a lot of pressure to push that water through that very tight membrane. Well, the cost of that pressure has been an obstacle for seawater desalination. Well, now we have technology has advanced where we have energy recovery devices that are very, very, very efficient. We can recover about 98% of the energy that we put in to push that water through the membrane. We can use that energy back, and so that's reduced the cost of desalination energy by about 50%, 49 to 50%. So those two things have really started driving seawater desalination. So now, for a couple reasons. One, the costs are now competitive. And also, the need for water, for fresh water, especially in places like Israel and the European countries where they don't have the fresh water supplies. This is a viable alternative. So you see how plants are starting to spring up. Talking a little bit about how the process works. It's called reverse osmosis. And what we do, we start out with osmosis, and that's a natural law. And what the natural law says is that if I have a water over here or a solvent over here that has a high concentration, and I have a solvent over here that has a low concentration of minerals in it, then the natural law is that this water here will try to dilute the water that has a higher concentration. It tries to make it in equilibrium. And it actually applies a force to do that. That's called osmotic force. Your body does that. in your ordinance? Well, what we do when we go through desal is we take the higher concentration of salt water, we apply pressure to it to push it through a membrane into a less concentrated water. And so not only do we have to force all that water through the very tight membrane, but we have to overcome the osmotic pressure of that. So that's why it's called reverse osmosis, because we're reversing the osmotic pressure on it. So we just take we take high pressure, high concentrate, push it through that membrane into a low concentrate water. And that's the water that we have as permeate or the drinking port of the water. This is just an illustration of the kind of how tight these membranes are. These are, that's a 1 micron size particle. And we have membranes that are called microfiltration, ultrafiltration, nanofiltration, and then we have reverse osmosis. And you see this reverse osmosis membrane, we're trapping these ions. They don't even get through it. The only thing that will get through it is small molecular weight, like water molecule. How a membrane plant works is we have pretreatment. We take it from the ocean here. So we take an intake. We take it through pretreatment, usually filtration, like they do at a conventional water treatment plant. And then we take it up to these reverse osmosis membranes. These are just very tight membranes, tight particles that we're going to push that water through. And it's only going to let water go through. Everything else is going to be trapped behind it. What's trapped behind it is called brine. And that's what we reject, is this brine solution that goes out into the ocean. We're going to talk a lot about that because that is the environmental consequences of desalination. And that's where we want to really get the facts out. Okay, so, but then the clean water, where all the particles are taken out, goes into pre-treatment or post-treatment. Because we took all the minerals out, your body still needs minerals. So we don't want to take everything out of the water. Also, it lowers the pH, so we want to adjust the pH. We want to add some stabilization chemicals, some alkalinity back into the water, and we want to add maybe some Mg and calcium back into the water so that we have a healthy blend of water. And then on the pretreatment side, the stuff that we take out of the pretreatment, we haul to landfill. A lot of that includes heavy metals. So we're actually cleaning up some of the water by removing heavy metals back to the landfill. This is kind of how a seawater membrane process works. For, and I'll just give you an example. For every gallon that we get out of water that we can drink, that we can use, it takes 2.7 gallons of seawater. So we have 2.7 gallons of seawater coming in. We got 1 gallon of water that we can use, and then we have 1.7 gallons of water that we have to discharge to go back into the receiving ocean that we do. Now, I did an example for a 20 MGD treatment plant. That's what we're designing in Corpus Christi, is a 20 million gallon per day water treatment facility that takes seawater and turns it into drinking water. Out of that 20 MGD, we're going to take 54 million gallons per day of water out of Corpus Christi Bay. And actually, this is in the Inner Harbor, if you're familiar with Corpus Christi. So we're going to take 54 million gallons out. We're going to add 20 million gallons back into the water distribution system for everybody to drink. And then we're going to return 34 million gallons of the salt back to the ocean. Now, it's pretty important. The desalination process does not add any salt to the ocean. So there's been a lot of articles saying a desal plant puts salt back in. It doesn't add any salt. Matter of fact, we don't return all the salt. We return about 98% of it. So, but it doesn't add any salt to it. But what it does do, it does concentrate the salt. So in this one, we may have a salt level of 31,000 milligrams per liter. Here, we may have 50,000 milligrams per liter. So just concentrate it into a smaller flow stream. And that's what we have to worry about, because aquatic life does not like to have rapid changes to the salinity. So we're talking about that. Let's talk about some of the plants that are operating and have been operating for time. These are the plants that in the United States where we have operating seawater desalination plant. California has the most. They have, these are the, what I call the major plants. They have some smaller ones too. But Santa Barbara, Huntington Beach, and Carlsbad. Carlsbad is a 50 million gallon per day facility, and it's been operating since 2015. And then Tampa Bay is the oldest facility in the United States, and it's a 25 million gallon per day, and it's been operating since I think 2007. And then in Corpus Christi, we have an industrial plant that's operating now, or actually starting to operate. And then also, we're applying for permits for it right now. This is the Carlsbad San Diego water treatment plant, where it produces 50 million gallons per day of water from the San Diego Bay area and then into San Diego. And it comes in and it's co-located with an existing power plant. And so it's using the existing power plant as blending for its discharge. So what it does, it takes intake water from the actual discharge of the power plant, goes through the reverse osmosis processes, and then returns the brine reject, the salt they took out, it returns it back to the discharge from the power plant. And this does a lot of good, because what it's doing is taking this concentrated discharge of brine and it's blending it with about 200 million gallons per day of reject from the power plant. Power plant's a one cycle through power plant. So by doing that, we're taking the high concentration and we're diluting it back down to a lower concentration. And as everybody knows, it's solution to pollution is dilution. So we are diluting it. What also is happening in the Carlsbad plant is the power plant is going out of operation. And so they wanted to maintain the same dilution ratio. So what they're requiring the Carlsbad plant to do is, instead of the power plant goes away, they still have to pump that much more water for blending. So they're actually blending by recycling the same intake that the power plant will use. The power plant's not there anymore. But you're getting the same amount of dilution from it. And this is the Tampa Bay. And Tampa Bay is a 25 million gallon per day facility, and they're doing the same thing. They co-locate it next to a power plant so that they can use that power plant for dilution of their discharge. And on this one, they have a tremendous amount of dilution, 1.4 billion gallons in that power plant. So it's a 25 million gallon per day facility. So even if you put about 50 million gallons per day of brine in there, it's lost at 1.4 billion gallons that you're diluting it with. So by the time it gets back to the bay, there's hardly any difference between it and the normal bay water. And so that has worked out pretty well for them, as long as you have a power plant to do that. What our concerns were in Corpus Christi, when we first looked at this in 2004, we did look at using their power plant. They have a Barney Davis power plant. But when you really look at things, power plants are really going through a phase where a lot of power plants are being phased out. And so if you depend totally on that power plant for dilution, you may not have it in a few years. And so we didn't want to go that route. This is at Corpus Christi. This is one of the first desal plants that's being built in the state of Texas. And this one here is an industrial plant. And what it does, it's a polymer manufacturer. They first started out with one company, and went bankrupt. Now they're into the second company, but they're still working on it. And what it is, it's a 22 million gallon per day industrial facility. They do not have to meet drinking water standards. They're using it for their processed water. So it's much more relaxed regulations for it. But it is a seawater, and it is discharge permitted. That's an important part. Their discharge, which is 38 million gallons per day, is already permitted for operations. Not operating, but it's permitted. This is what we're doing for Corpus. Corpus is really hitting it hard because Corpus has this plant here is under construction, the industrial plant, and it's already about 80% complete. Then the city of Corpus Christi is applying for a permit in the Inner Harbor Ship Channel, and that's what I'm working on presently right now with the Texas Commission on Environmental Quality. We all have also, the city, applied for La Quinta Channel for a 30 million gallon per day plant on La Quinta. At the same time, the Port of Corpus Christi, a separate entity from the city, has applied for 2 locations. One is close to ours on La Quinta, it's the La Quinta Channel for the port, and then also the port has for the port, that's the ports, and this is the cities, that's all right. And then they have one at Harbor Island, and at the Harbor Island is a 50 million gallon per day facility they have applied for. And all 4 of these are going through permitting processes right now through TCEQ. And so that has been a long process. And since this is going to be the first municipal seawater plants in the state of Texas, TCEQ is really taking their time because they don't really have any regulations for it because this is the first ones that are permitting. So we're helping them develop regulations by looking at regulations from California, from other countries on how they handle this. And also the main issue is protect the environment, protect the aquatic life. Part of the Texas regulations allows you to use all dischargers that discharge anything, wastewater, any kind of discharge, have what we call mixing zones or regulatory mixing zones. And so what TCQ uses, they use 3 different types of mixing zones. One they call the ZAD, Zone of Initial Dilution, and that's a 50-foot radius from the discharge. They want you to allow whatever you do to be mixed because all our modeling is really based on dilution. And so you got to get it out into the water so it starts to dilute. And 50 foot is a pretty small radius. 25 foot out that way. It's 100 foot. It's a 50-foot radius, so it's 100 foot across. It's a fairly small area. And so that they call the zone of initial dilution, or they have certain criteria. One is the aquatic life criteria, which is called an LC50. So they said, in this zone here, you have to have at least 50% survival of certain species. And so you have to do what we call a wet test, cholecystoscopy test, to make sure that you're meeting that criteria. When we get up to the mixing zone, which is 200-foot radius, then you can get down to what they call chronic conditions for aquatic life. That means they have to maintain the same body weight. You have to have the same number of broods on for each of the species that we're selecting. So there's a lot of other criteria that you have to meet. And then when we get down to 400 foot, we have what we call human health criteria. So we have to make sure that nothing is going to affect human health if anybody decides to take water from that radius point out there. So that's the regulatory mixing zones. Now we get down to where we have the water. This is our actual discharge. We have what we call 30 MGD for the Inner Harbor maximum and a 40 MGD for La Quinta maximum. And we have what we call recovery rates. And that's just how much of the water we think we could recover. And these particular membranes operate between 40 and 50%. So we could have a 40% recovery rate, or we could have a 50% recovery rate. But what we get down to, this is the effluent from a 30 MGD. If we had 40%, we would have an effluent quantity of 51.47 we had 50% recovery, we'd have an effluent of 35.17 MGD, and then the effluent of the salinity that we discharge is 49.9 parts per thousand, or that's 49,900 milligrams per liter, and then the for 50%, not working, but 50%, it's 58.4 parts per thousand. But what I want you to look at is, once we're out through the 200-foot radius regulatory mixing zone, we're at 33.84. We've already diluted that. And then the actual ambient is 31.59. So the difference between those two is about 1.6 parts per thousand difference. So if you know anything about salinity, that's not much difference between 1,600 milligrams per liter when you're in 31,000 milligrams per liter of salinity. Our temperature doesn't really change, it's less than 1.5. Our dissolved oxygen is supersaturated, so it's up 100%, and then the pH is set by regulations between 6 and 9. Okay, I'll cover it really quickly here. What the environmental concerns are for desalination plants, there's 4 of them. The first 2 are to do with the intake, impingement and entrapment. They don't want you to trap aquatic life on your screens, the intake screens, and they don't want you to suck them in to the system where they die. So those are the 2 that we have to deal with. What we're doing with, we're putting in what we call wedge bar screens. These screens have a velocity intake of less than 0.5 feet per second, which is about 0.3 miles per hour. You can walk faster than that. Fish just swim by it. So you don't have any pulling force to trap them on the screen. So we have, in essence, removed all of the impingement requirements that EPA wants. This is called best available treatment technology. Also, we have a screen opening of less than 0.2 millimeters. What we're doing corpus is 1.75 millimeters. That's the thickness of a dime. And that traps 99% of all the aquatic organisms that might be floating around out there. So we have, using EPA standards, we have eliminated both entrapment and entrainment. The other things that we have to worry about from a regulatory standpoint are, 1, hypoxic conditions. This is where, when you put more salinity into the water, it will reduce the water's capability of dissolving oxygen. You had a glass of water and it had no salinity in it, you'd have about 9 milligrams per liter of oxygen in that water naturally dissolved. You put 31,000 milligrams per liter of salinity in there, now suddenly we're down to about 6 milligrams per liter of oxygen dissolved. So the salinity actually reduces, and if you reduce it low enough, you get hypoxic conditions in their organisms. They need the oxygen. The other issue is with osmotic regulation. As we went through what is osmotic pressure, and aquatic life has that too. If I increase the salinity outside of that fish higher than what the salinity's been, that can actually suck water out of that fish. It will dehydrate it. And so you don't want to get such high salinities that we actually overcome the natural ability of the organism to do osmotic regulation. Okay? So those are the 2 that we need to address. What the old method of disposal was, and where desal got its bad name, was from open discharge methods, where Bill had a picture of the Monaco plant where you can see the brine go straight out into the ocean. That's an open discharge. And what an open discharge does, it's a heavy brine, 50 to 60 milligrams per liter. And when it does, it doesn't dissolve. It stays heavy brine. It goes down there, and because it's a high salinity, it dries out all the oxygen out of the water and creates hypoxic conditions, or could create an hypoxic condition. And we don't want that. But there have been these created by this O method, and so what we had to do is come up with a better way to do it. And we did. This is the better mousetrap. This is jet diffusion. What we're going to do here, we're going to take the brine and we're going to inject it with high pressure jets into the water. And when these jets go into the water, they disperse very rapidly. And so we dilute really, really quickly. So at 25 feet distance, we're less than 0.5 feet per second velocity coming out. So the velocity dissipates very quickly. We have a maximum increase in salinity at 50 feet of 2.9. We have a maximum, we can take brine reduction at 50 feet from 58.4 down to 34.9, and ambient is 31.59. So we can rapidly get this down to ambient condition, and it doesn't stay as a dense brine anymore. It's completely dispersed into the ocean. And this is a graph shows what it is. We use a model called Cormix by Cornell University, and you can see when we discharge, we're at 100% effluent, and you see this is 50 feet. At 50 feet, we're at 11% effluent, and the further out you go, the effluent starts diffusing out. So if we're far enough away, when we get down to the 400-foot human health criteria, we're down to 6.1% effluent. This is velocity. To show you how the velocity dissipates very quickly. At 25 feet, we're dropping down to well below 0.5 feet per second. And these are kind of our final numbers that we came up with. We have the permit conditions. We're at for 20 MGD in Ann Arbor. We have a discharge of 34.3% or 34.3 million gallons per day. We have a maximum of 41.2. We increase at the zone of initial dilution, a 50-foot radius. It will increase the salinity by 2.8 parts per thousand. So we're going from 31.59 parts per thousand up to about 33.4 parts per thousand. So a very slight increase in salinity. But by the time we're down to what the regulatory people look at 200 foot, we're at 1.6 parts per thousand increase in salinity. Okay? Which is not a very large increase. And if you also look at what we had, we took the historical data of salinity for Corpus Christi and Ann Arbor over 30 years. And this is kind of the range between the 5% and the 95% numbers on it. And so you can see how salinity naturally varies a lot. And so if you have a 1.6 parts per thousand variance in there, that's not even going to come close to the natural variance that the bay has with any seasonal change or any direct or any change. And so for conclusions, I'd just like to conclude that seawater desalination is drought-proof and allows to tap into the other 97.5% of the water, the oceans on this planet, which is going to be important. Seawater desalination is affordable if the plant sizes are selected appropriately. Energy costs are reasonable and will improve with renewable technology, and that's what we're also looking at is doing solar and other types of renewable technology, even wind. Seawater desalination is environmentally safe if plant intake and discharges are designed appropriately. And science and technology developments are likely to result in future reductions of energy use and cost for producing desalination facilities, which I think we're going to be faced with in the future. We're going to see more and more desal plants come. It just needs to be done in the right way. With that, I'll open it up to questions. Yes?
What percent of Corpus Christi's needs for potable water with the 50 million gallons they
They're using it. We do take care of a pretty good chunk of it. Right now, their existing usage around 200 million gallons a day. That's what their plant's rated at. They're owning that Stevens water treatment plant. Another 50 is looking at industries that might move in and other industry uses. So they think it's going to take them out to the 2050 guideline, period. Yes?
I'm sorry if this is a stupid question, but does the water have to be a certain temperature for desalination?
No, it doesn't. Matter of fact, well, that's a great question. Matter of fact,
Really?
and one thing I didn't have is a great question, is that one of the reasons that initially, when desalination first started, they wanted to look at putting them in cold disposal with these power plants. Because once through power plants, what they're rejecting the hot water or the warm water out of the power plants. Warm water is really good for desalination because it's membranes. This membrane works on viscosity of water. As you remember back in your chemistry days, the viscosity is proportional to temperature. The lower it gets, you go down to ice, it's very viscous, or you go up to steam that's not viscous at all. So the warmer it gets, the less viscous. The less viscous it is, the easier it is to push that water through that membrane. So the warmer the water, the better. It will operate over the entire temperature range that we have in Corpus Christi, but it will operate more efficiently at higher temperatures. So we like to operate it during the summer because it costs less, and in the winter it costs a little more because of the viscosity of the water.
How about Anchorage, Alaska?
Huh? Oh, that it will still operate. It was when you have colder water, those operating costs are going to be higher than warmer operating water costs. Does that make sense? But it will still operate. It's just we like to kind of hit that sweet spot where optimization is, the cost. Yes.
We know that they drill for oil in the Gulf. So
Yes.
how would discharges or leaks from those systems affect this process?
Ooh, I don't know. That's a great question. I don't know how leaks from those processes would, but one of the things that we did look at, and one of the things that a lot of people are looking at desal, is getting rid of this brine. And before, when they had this open discharge, that's an issue because it will create that hypoxic condition. It is very heavy, very dense. What they looked at before they really came up with jet diffusion is saying, okay, we'll take that brine and we'll do deep well injections with it. We'll do the same thing the oil company does with it. We'll even find some abandoned oil wells and re-permit those and do that. But with this jet, you don't have to do that.
Thank you.
Yes.
It seems like the key for the whole thing is this membrane.
Yes.
Can you tell us a lot about the membrane? A couple of questions that are bugging me.
Okay.
Is what does it cost? How often do they have to be made over again?
Right.
And how much energy goes into making these membranes?
Okay.
We've heard a lot from the green people about how great electricity is, but we're finding out that it costs a hell of a lot more in terms of energy to manufacture electrical energy.
That's correct. That's correct.
What about our membranes?
Yeah. First of all, they have a fairly low carbon footprint to begin with. But just to answer your question, first off, the membranes are polymer-based sheet membrane. Okay, so they all have their own patented design, but it's just a sheet that's made out of basically polymer. And that's why you can't use polymer in your process because it would get mixed up in the membrane. So we have a very tight, fine, synthetic membrane polymer sheet. That's what makes a membrane. I'm sorry, what was your second question?
Well, how green is it?
How green? It doesn't take much to manufacture this. The membranes itself cost about $400 for an element. And you have an element is something around a 2-foot length of these membranes, and we put different elements in what we call vessels on the thing. But it's about $400 to manufacture, so it's not super expensive. But you did have a very good question about how long do they last, and we have to factor that in on calculating the total life cycle cost of these membrane plants, because these things do. You can imagine we're thinner than a human hair, 1/1,000,000th of a human hair. We're pushing all this stuff through it, and it's trapping it. That's what its job is, to trap it. Okay. Well, what we do, we clean that membrane about every 30 days. We use a chemical cleaning. We use a caustic cleaning to clean that membrane. So we take it out of service, we flush water through it, we rinse it, we put the chemicals in it, so we clean it out. Matter of fact, all these chemicals that we use for cleaning, we're going to capture that in tanks and haul it off. We don't discharge it again. It's all separate, so we don't want to get that back in the ocean. But we clean these membranes, and then we measure what we call the recovery rate of that membrane. So when we clean it, we may put it back in service, and it may only be operating at 80 or 90% of its original efficiency. Okay, and the efficiency is the amount of chloride salt that we're rejecting. Okay, and as it starts rejecting more and more chloride salt, normally the manufacturers will guarantee this membrane to meet the requirements for salt rejection for up to 7 years. So after 7 years, you have to replace these elements with new membranes. And we factor that into our overall life cycle cost. So when I calculate at $4 per 1,000 gallons, that includes replacement costs actually I used every 4 years. So I just wanted to be conservative. So every 4 years, I'm replacing all these elements in these membranes. Okay.
And this polymer is made out of petroleum?
Polymer is made out of, yes, it's a petroleum based.
Are we going to get our petroleum from Russia?
I hope not. I hope not. And I know at Corpus Christi they have a lot of petroleum manufacturers, and they're building this big polymer plant there because of the availability of the product to make the polymer. Yes?
What about the corrosion of the pipes and stuff, and replacement of those?
Replacement of the pipes, I'm sorry?
Of the intakes.
Corrosion.
Corrosion. Oh, corrosion's a big issue. Because salt water, you get corrosion, you get chlorides, and they eat everything. And so what we do, we make these as corrosion resistant as possible. We use a lot of PVC pipes, high density, polymer density pipes, HPED pipes. So we use low corrosive material for this. All the membranes and the vessels that they're in, they're all corrosion resistant. There's not even corrosion there. Yes?
Despite all the good progress that's been made in reducing the energy use, it's still a really big energy consumer.
It is.
And I wonder if any thought has been given to storing some water and taking the plant offline in the event of a statewide energy crisis of the type that occurred last year.
Yeah, I'm not sure how the state's going to handle that, or yeah, we had a big crisis. So that's kind of, in my mind, similar to what we do under our drought contingency plans. In our drought contingency plans, we have a hierarchy of users, and they say, okay, if we run out of water, these users down here, commercial, are going to get cut off first. And then if we still run out of water, industries. And then finally, residential is way up here. And so they may do the same thing. They don't have that now, but they may do the same thing with electric power to say, okay, California, I know, has had a lot of grid problems with their energy usage on this thing. But yeah, the plants can be, that's one of the neat things about RO plants. They're modular construction. We build these things what we call units. And so we might build a rack that has a certain number of elements in it, and we can take these racks off as we want to, or we can add racks to it to increase the capacity. So it's very flexible. But also, it's very different than operating the water treatment plants that we have here in Georgetown. Where the operator goes out there, we have clarifiers, he can take the water, he can look at it and see the flock that's built up in it. He can make sure everything's working good. He sees it. He can take it to the laboratory and then test settling and so forth. But you can't really do that on a membrane plant. Membrane plant's pretty much automatic. Because of this membrane, and you've got a barrier, and we can measure the effectiveness of that barrier because we are monitoring that, but you don't actually see the water. It's all enclosed pipes. Yes.
What is the typical price for water, around Texas? How much they paying?
That's a great question, and that's why I think a lot of people get confused, because water depends not only on the treatment plants, but it depends on where you get the water and how much it costs you to bring the water to the water treatment plant, and then build the water treatment plant, and then take it out to your water distribution system on the thing. So a normal plant, like in Corpus, the O.N. Stevens plant, that has to get its water from two reservoirs, it's got Chunk Lake and then Corpus Lake, and it also has 158 miles away water from the Colorado River. That's all very expensive water to bring in to the plant, and by the time you do that, it's about the $4 per 1,000 gallons. So it's very close to the cost that it would take to develop a new water supply. Yes.
I'm curious about that. The final result after it's been discharged at length still is a 1.6 increase parts per unit of salinity. Is that about right?
When we discharge it back into the ocean,
Right.
yes.
So I'm just curious how that compares, for example, to the discharge of the Mississippi River that has created that very large dead zone out in the Delta. That also is primarily salts, and that is doing that. So how does that 1.6 increase in the salinity parts per unit compare to the discharge from the Mississippi River that has created this dead zone?
I don't know. I haven't seen any person. I know 1.6 is really, really small. I mean, I've done a lot of research into aquatic life, and I've looked at what the tolerance of salinity is to the juveniles and adult species, and a 1.6 increase in salinity. I haven't found any species that are sensitive enough for that to make a difference.
Thank you.
Yeah, well, one point is that the problem with the Mississippi is organic matter settling out.
Yeah, and its turbidity and its settlement,
It's
a lot of, right, yeah.
Around
Yeah.
large ships like cruise ships desalinize water.
Right.
They use the same process that you're.
Use the same process. They use the same, they don't use the same discharge process. So they are allowed to just dump it back into the ocean.
Is there moving?
Because they're on the ocean. Because in the open sea, there's really not any standard regulations to control that. So I think that's the reason. Yes.
So, will this plant work like 24 hours a day? In other words, like, will high or low tide make a difference in the inner harbor, that will have less water at low tide, so the amount will be different than it would be at high?
Great question. The tide really doesn't make a difference. I mean, we're going to take the intake. The intake's going to be 20 feet below low tide.
I mean,
So-
I'm talking about discharge.
Oh, our discharge?
Yeah.
Our discharge is going to be 34 feet under the low tide. So we're discharging, here's a tide that goes up down. We're discharging down here. And we're discharging down here with these jets. And these jets shoot up, but they don't go all the way to the surface. So they won't go all the way up to where the tide has an impact on it. And after we modeled out in the 400, 500 feet that we're supposed supposed to bottle out too, and there's no impact. So we don't get to the surface. So if you're standing there at the surface, you won't see any ruffles or any turbulence by these jets. They just don't get out that far.
Will there be oversight just to check it once it's open?
There will be. TCEQ has a tremendous amount of reporting on these things. So they issue the discharge permit, and they have a required reporting on all this stuff. We will report all the stuff that they want reported. Plus, we do quarterly biomonitoring tests, and we actually take these species and we actually put them through effluent testing to make sure that they meet all the conditions that TCEQ wants. Yes?
Mike, you had said something about, if I understood you correctly, that there was energy recovery. How does that work? Because you've got a pump that's pushing, and how do you recover energy, if I understood you correctly?
You do. Yeah, this is the thing this is one of the key things that made desalination is that we have to push a lot of energy through that membrane. Matter of fact, almost 1,000 pounds per square inch. That's a lot of pressure, okay? But that 1,000 pounds per inch is on this side of the membrane. This side of the membrane here, the membrane eats up all the pressure, so we only have a couple bars of pressure on the other side. So, but we got 1,000 psi right here, okay? What we do then, we take that goes out with this brine reject. We have a device that we capture that 1,000 pounds, and it actually is a spinning device that recovers it. And once we recover that, it converts that back to pressure, and we put that back to the pump that's pumping up this 1,000 pounds. And so it's kind of a circle that goes around. And it will recover 98% of that 1,000 pounds. So I put 1,000 pounds on there, it will recover 980 psi out of that. That goes back to the pump that's pumping up there. So that pump only has to pump about 20 psi is all the pump has to pump, because we're recirculating that. We're recovering that energy. And I can send you the specs on the device. It's a patent device, but it works well. All modern plants are now using it on the thing, but it's recovered a tremendous amount of energy because of that.
I don't need the specs, I'm not sure I even understand them.
Yes. Yes,
You mentioned cleaning the membrane.
right.
And the chemicals used to clean it
Right.
are spirited away. Where
Right.
do they go?
Thanks. we take them two places. First of all, what we like to do is take them over to the wastewater treatment plant. We neutralize them because we have some caustic, might have a high pH, and so we'll get with the city, say, can your treatment plant take this? And this is not a big quantity compared to, they have 8 million gallons per day coming into the treatment plant. This may just be a few 50,000 gallon container. But anyway, we will take it over and say, can we discharge this at your treatment plant if we neutralize it and will not harm any of your activated sludge processes you use in your treatment plant? That's the first choice. That's the easiest thing to do. If they say, no, we don't want that, it might harm us, we don't want to go through an inhibition study, well then we will take that to, they have haulers that haul off hazardous material. And so we will have a hauler take it to an approved hazardous disposal site. And so those are our two options. First option, we'd like to just dump it to the wastewater
So
treatment
at
plant.
that hazardous disposal site, is
Right.
it just stored?
I'm not sure what they store it. Some of them store it, some of them they treat it. Some of them they do other things with it. But it's an EPA approved facility that we're taking it to.
I have another question.
Yes.
The jets.
Yes.
That has got to be environmentally not conducive to sea
The jet's right next to, now you saw after 25 feet, it goes down to where it is safe. Goes down to point. Everybody, every environmentalist and also EPA have agreed that if you keep the velocity below 0.5 feet per second, it is safe for aquatic life. So that's 25 feet. So at 25 feet, we're down below the 0.5. Got two options. At 25 feet, this is what we're still studying. We can put up fish nets so that we can keep the fish away from that 25 feet jet. And so that may be what we end up doing. Or we could say, okay, what harm would it do? How many fish are in that 25 feet? And actually do mitigation. Say, okay, we'll take, if it's going to kill 5,000 fish a day or 2 fish a day, I don't know what the number is, well then we will go ahead and set up some kind of nursery or some other fish habitat, and we will go ahead and mitigate whatever that damage is. So you can either mitigate it or you can prevent it. And so it's usually fish nets, or you set up some kind of beneficial habitat area that you contribute to. Yes?
Is this going to be something that it's just for the use of the city of Corpus Christi, or is there a potential they can ramp up that they can sell it to other places?
I think there's always potential to. What I see happening in Texas, you can see we're running out of water. There's no more really good feasible places for reservoirs in Texas anymore. I think we've kind of built the last more reservoirs. And so what I think is going to happen is people like Corpus Christi, Houston, other Gulf, Freeport, other Gulf cities are going to start building seawater desalination. They also have upstream water supplies that they have. By building a seawater desalination plant, they could potentially release some of their upstream water rights for other people to use. And I see that happening. And then, eventually you could even go a pipeline up to the Dallas-Fort Worth area. But first of all, I think it's going to be done in stealth. It's going to be, we have water down here. We got water in some of our upstream reservoirs that you guys can come down to. That's a lot closer for you. And then we will water trade. Let me buy into that, so since you could also then pay for our desal plants.
I was a groundwater conservation district director at one point in time, and so the whole right capture, where are we taking from one to give to another, and so this is exciting to see.
It's very exciting. I mean, we have got solutions. There's no questions. We have to come up with some unique solutions. I think one of the things that Americans have been really good at is innovation, and so I can see us. And if we can ever reasonably tap into the seawater and get functioning facilities, I think our water issues will start taking care of themselves. Yes.
In the San Juan Islands in Washington State, they've been doing desalination there probably for 30 years, but they're independently owned. And they would cost the homeowner probably 4 cents a gallon of water.
Well, yeah.
Any ideas what this might cost?
Well, like I said, we did the cost. It's $4 per 1,000 gallons, for 1,000 gallons. Yeah. Now, there's also in Texas, we have what we call a lot of brackish water. If you're over in Brazos, Possum Kingdom is brackish. They have RO plants on it. Lake Granbury is brackish, and it has desalination plants on it. Lake Whitney is brackish, so forth. So we have a lot of brackish plants. Matter of fact, the largest brackish plant in the United States is groundwater, and it's in El Paso. It's a K. Bailey Hutchinson desalination plant where we take brackish groundwater and we're treating that. It's a lot cheaper to treat brackish groundwater than it is seawater, because seawater is 32,000 milligrams per liter, brackish water is 10,000 or 8,000 milligrams per liter, so it takes a lot less pressure to treat it, and so we can treat it on it. But the disposal, what they have to do in El Paso is once they take the salt out, it goes into deep well injections. So when we go down below to where we find an aquifer that's got 10,000 milligrams per liter in it, and we inject it in that. Okay, I probably have taken more than my time, I'm sorry. But anyway, I enjoyed it. I hope you guys have learned something from this. The whole point of this was kind of get